We've learned that the Riemann sum is an approximation for the area underneath the curve. But is it possible for it to be exactly equal to the area underneath the curve? This is climb time, and in this video, we will look at the integral as an infinite Riemann sum. So what I have here is a function, f of x, and I'm looking at an approximation of the area underneath the curve by using four subintervals, four rectangles. And so what we know is that the integral of fx dx from a to b is two things. One, it is an antiderivative, and we'll look at that later. And two, it is the area underneath the curve. And when we say that, we mean the area between the function and the x-axis. So it can be approximately equal to a Riemann sum. And a Riemann sum is where you try to find the area underneath the curve by breaking it up into rectangles of equal width. So here I have four rectangles of equal width, and I'm using the left endpoint to find the height of each rectangle. So you can see the left endpoint represents the height of each rectangle. And so it's approximately equal to the area underneath the curve. So let's kind of play this out a little bit. So the Riemann sum is an approximation for the area. And what the Riemann sum equals is the sum of four areas, A1 plus A2 plus A3 plus A4. And that represents four rectangles, 1, 2, 3, 4. All right, so what is the area of each rectangle? Well, each rectangle has a width, and I'm going to call the width delta x. And I don't know that I'm going to fit all this in one line, but that's okay. I'll extend it to two lines. So every rectangle has a width delta x, and every rectangle has a height. And the first height is going to be f, what I'm going to call x0. So what that means is my very first height right here, that y value right there is going to be f of x sub 0. That's the very first height. And then the next rectangle is also going to have the same width plus delta x, but the height is going to be x sub 1. And then we're going to keep adding. So we have another width and another height, x2. And then we have another width, we have another height, x3. All right, so there's our four rectangles with their four areas, width times height in each case. And so probably you can see that this is going to be x1, this is fx1, this is fx2, and this is fx3. Let's see if I can show the last one there, f of x3. In fact, we could have a fx4 as well, and that would be if we use right endpoints instead of left endpoints. But fx0 is this first one, then fx1, then fx2, then fx3. And that's all the heights we need. We need four heights. And if we're using left endpoints, we'd end at fx3. If we were using right endpoints, we'd end at fx4. All right, so now what we're going to try to do is simplify this into a formula using summation notation. So summation notation looks like this. It's a sigma, and sigma is sort of like the associated with sum, classically in statistics and mathematics. And so delta x is going to be in every single term. So what this means, we add up a bunch of terms, and delta x is in every single term. And then what else is in every single term is a y value. And so I'm going to say sub I. And so my y value is going to change. It's going to start. And down here, I'm going to say where it starts and where it ends. It's going to end at 0. And I'm sorry, it's going to start at 0, 0, 1, 2, 3. And it's going to end at 3. All right, so that is what it looks like when written as a formula. Now, the advantage of writing it as a formula is that if we wanted more than 4 terms, we wanted 10 terms, then we can easily just change the formula. We don't have to write them all out. Once you see how it works as a formula, it's very easy then to just adjust the formula. Also, the tedious part of finding Riemann sums is actually finding the individual terms. So if you can break it into a formula, you can let a machine do the tedious part, and therefore you can get your area to be more and more accurate with more and more rectangles without doing the tedious part yourself. So it's very advantageous to break it into a formula using summation notation. All right, so now what I want to do is I want to make this a little bit more general. Let's assume now that it's not just 3 rectangles, but it's any number of rectangles. So what I'm going to do, and what do I change if I want this to be more than 3 rectangles? all I have to do is change 3 to 4 or 5 or 6 or 7. I just add more rectangles. Now, keep in mind your delta x will change and your xi will change. So maybe before I do that, I'm going to show how these delta x and the x sub I depend on your basic information. Your basic information is going to be the function itself, where you start, where you end, a and b. And then they also depend on the number of rectangles. So in this case, so no rectangles equals 4. So it should depend on n, f of x, a, and b. That's all it should depend on. So let's see if we can, I'm going to go ahead and change this to n right now. So I'm going to start at 0. I'm sorry, it's not n, because before n was, we had 4, 1, 2, 3, 4 rectangles, but we stopped at 3. So it's n minus 1 on the top. So we don't go to the very last one. I'm going to leave delta x, but I'm going to explain what delta x is in a second. And then let's look at what x sub I is, because there's a pattern to x sub I. We start at a, then after a, we're going to move one delta x over. And then after a, we're going to move another delta x over. Then after that, we can move another delta x over. So each time you're moving one delta x over, so there's a pattern to that. So we can actually put in the pattern right here. We can say, hey, we're starting at a, that's our starting point. And then what we're going to do is we are going to move one delta x over for every new term, for every new rectangle. So delta x times I. Okay, and I'll put a little time sign there. So times I. So that means when I equals 0, I plug in 0 for I. That means there's no delta x initially, and I start at f of a. When I equals 1, that means I'm going to move over. I'm going to start at f of a, but I'm add 1 delta x. When I equals 2, I'm going to start at a and move over 2 delta x's. So this is how we move along. We just add increments of delta x. And by saying I equals 0, we know that I increments up 1 each time. Each term will have a x value, our x sub I, that's going to be 1 delta x over. I should show it this way. Yeah, 1 delta x over. I keep thinking that if I go this way, it's going to look correct to you, but it looks the same for me and for you. So as I go to the right each time, I will get 1 delta x beyond a. So I start at a when I is equal to 0. And then when I is equal to 1, I'm a plus delta x, which means I'm going to be 1 delta x over. And then when I equals 2, I'm going to be a plus 2 delta x's. So a plus 2 delta x's, 2 delta x's over. When I is equal to 3, I'm going to be 3 delta x's over. So 1, 2, 3. And that's actually my last function value. So this is what our formula looks like. Now we want to remind ourselves that this is going to be using left endpoints. This is left endpoints. And so we're using our example from left endpoints. I do also want to talk about what delta x is. I'm going to do this over here. Delta x can be defined very easily based on where you start, where you end, and the number of rectangles. So the difference between where you start and where you end divided by the number of rectangles is going to be delta x. So delta x is defined. It's defined based on initial given information. What is your overall width that you're trying to find the area of, and how many rectangles you want to use? So if you want to use 100 rectangles, then delta x is going to be a lot smaller than if you use 4 rectangles. So delta x is defined in terms of b, a, and n. We'll know our function value ahead of time. That's a known thing. And we'll know a and b. So this is completely dependent on a, b, the function, and the number of rectangles. Okay, so that's what it looks like for left endpoints. I want to look real quick at what it looks like for right endpoints. And so for right endpoints, let's go ahead and use pink again. So for right endpoints, we're going to just change one thing. That's what's so nice about this. You just have to change one thing. And the only thing you have to change is where you start and where you end. So you're still going to have the same number of rectangles for right endpoints. You're still going to have this exact same formula here. You're going to start at A, and you're going to move over increments of delta x each time. It's supposed to be times. Here, let me erase that. It's not delta x sub I. It's delta x times I. All right, and so you're going to move over delta x increments each time is I increments. The difference is with the right endpoints, you're going to start over one spot. You're going to start here. This will determine your first y value. and then you're going to end at B. So you're going to start one interval over, one subinterval over, and that's what will determine your first function value for right endpoints, and then you will end at f of B. Notice when we did left endpoints, we started f of A, but we didn't end at f of B. We ended one before f of B. So the only thing that changes is we start one to the right, and we end one to the right. And so all the middle terms are the same. It's only the two ends that change. So when using left endpoints, you're using the far extreme left, but you don't make it to the far extreme right. When you're using right endpoints, you start one over and you end at the far extreme right. So it's like it's just a shift of which function values you use, but all the middle ones stay the same. So all the changes is your starting point and your ending point. And this is your right endpoints. This is here is your right endpoints. So it's interesting how little changes between the right and the left once you get into a formula like that. All right, so now the question is, as we add more and more rectangles, all we got to do is make a bigger number for n. That's a beautiful thing about having this formula, is that we can put it into a calculator, we just change n, and we can find out the area for any n. And all the tedious work is gone. Let a machine do the tedious work for you. Now, can we make n so big that the area is exactly equal to the Riemann sum? And the answer is yes, we can, only if n equals infinity. So what we know is as n approaches infinity, the Riemann sum, that's supposed to be m, will approach the actual area. That's what we know to be true. So as n gets bigger and bigger and bigger and bigger, then that means the number of rectangles is going to increase. So the number of A's will increase. That means that that gap between the red boxes and the green graph will get smaller, smaller, smaller. And the difference will get to eventually zero, but only if we can, the only way we know for sure it's going to be zero is if n is actually infinitely big. So the way that we write this looks like this. And actually, maybe I'll use a new color for this because this is kind of an important takeaway here, that the limit as n approaches infinity of this right here, I'm going to use this one. I could use either one. It doesn't matter if I use left or right, because what we know is that the left and the right, one will be too big, one will be too small, depending if we're increasing or decreasing. I have another video on that. But as we add more and more rectangles, we know that they converge on each other. They converge on each other. And so the one that's too big gets closer to the actual area. The one that's too small gets closer to the area. And as they get bigger, as you get more and more and more rectangles, eventually they converge on each other and they equal the actual area. So if we can have an infinite number of rectangles, it doesn't matter if we're using the right endpoint or the left endpoint. So I'm going to use this one because I think it looks a little nicer than having n minus 1 on the top. So we say I equals 1 to n, and delta x is our width that you're going to have for every single rectangle. And then for your height, you're going to have a plus delta x times I. Okay. And then I'll also say where delta x is equal to b minus a over n. Okay, so the limit is n approaches infinity of width, that you can see that if n approaches infinity, the width gets infinitely small. And so delta x will get infinitely small as n approaches infinity, which basically turns delta x into dx. And as n approaches infinity means we have an infinite number of rectangles. And as we get an infinite number of rectangles and delta x is infinitely small, we actually end up getting function values that are very, 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 very close to each other. In fact, they are infinite close to each other. And based on how this works, we have no gaps or overlaps. So we end up with this. The y value is the height, and the dx represents the delta x. And this little integral sign looks like an S because it is the sum of all the infinitely small rectangles. So I'm going to go ahead and write that in. That this is actually equal then to the integral of f of x dx. So yes, the Riemann sum is actually equal to the area. It's not an approximation, it's equal to the area, but only if it is We have an infinite number of them. So can the integral be written as a Riemann sum and be equal and not just approximate? The answer is yes, but only if you have an infinite number of rectangles. This is actually the formal definition of the integral as area. It's a infinite sum of infinitely small rectangles.